Yeah, sorry. All right, well, it's my great pleasure to introduce Avi Loeb, who is currently the Department Chair of Astronomy at Harvard University, and interested in all sorts of things, is the founding director of the Black Hole Initiative, and is on the board of the Starshot project. Avi got his PhD at IfA University in Israel and spent a while doing plasma physics-related topics, particularly with things related to military defense in Israel, but managed to get convinced by John McCall to go into astrophysics and to come over to the Institute for Advanced Studies, and where he spent some time as a postdoc, and then went up to Harvard University nearly 20 years ago, over 20 years ago now, and has been at Harvard ever since. Thank you.
Thank you very much, Gene. It's a great pleasure to be here, and my talk today will focus on the habitability of the universe, but I should confess that Hawaii looks much more habitable than any other place I've been to. So perhaps this is the right place to give this talk. Yeah. So I'll start with a brief overview on the current status of the search for life on other planets. And in particular, there are different types of planets that are known that were found by the Kepler satellite and were looked at by telescopes on Earth. There are rocky planets, so what we have on the vertical axis is the size of the planet relative to the size of the Earth. And on the horizontal axis, the orbital period. So 1 year is right around here. And if we're dealing with a star similar to the Sun, that's roughly where the habitable zone is. And an Earth is just around here, so rocky planets occupy this spot. And of course, it's more challenging to detect planets that are farther out because of their small effect on the host star in terms of tugging it along, or the small likelihood of them passing in front of it. But planets that are closer in are easier to detect, and in particular through the transit method. There are different methods to detect planets, either through the radial effect, velocity effect they have on the host star. If they transit in front of the star, we can see the small diminution in the flux of the star, or we can actually image them. There are also microlensing searches for planets, pulsar timing, and the Kepler satellite populates a lot of this plane right now because it discovered the thousands of planets. And as you can see in this corner here, there are lava worlds, and I wanted to emphasize them in the context of Hawaii. I call these Hawaiian planets. They're basically planets that are molten, made of lava, simply because they were heated due to the proximity to the star or an impact by another object. The most direct way to measure not just the existence of the planet, but the mass of the planet is the radial velocity method, where the planet tugs gravitationally the host star. And you measure the motion of the star, the small motion, through the spectral lines. Obviously, the Keck Observatory was an important player in this, using this method, and promoting, pioneering the discovery of many planets over the past 2 decades. The other method is using transits, where the planet passes in front of the star and blocks a small fraction of the light from the star. And the Kepler satellite took advantage of this method to discover thousands of planets since 2009, when it was launched. And you can see the latest display of Kepler planets as of June this year. Just this plot was made a few weeks ago. You can see here again the size relative to Earth. Earth-like planets are here, and versus the orbital period. There are a total of 4,000 points on this plot. And you can see also Neptune size and Jupiter size. And just a couple of weeks ago, there was an announcement of 219 new planets from the latest Kepler observations, out of which 10 are Earth-like, in terms of their size and in terms of their location in the habitable zone of sun-like stars. And you can see those habitable zone planets in terms of the energy received by the planet, the energy per unit area on the planet, being similar to that on Earth. And this is the surface temperature of the star. You can see a star like the sun is right around here, and we are zooming in the habitable region. And there are 10 new planets that were found to have a size similar to that of Earth, maybe tenths of percent larger in some cases, and being at the right distance where the energy received by the planet is similar to that intercepted by Earth. And so liquid water could potentially exist on those planets. In terms of abundance, the work dates back a couple of years, where it was determined that about a quarter of all the dwarf stars, the most common stars are dwarf stars, much less massive than the sun, and about a quarter of them have Earth-sized planets in the habitable zone of those stars. We're talking about stars that are much fainter than the sun, and so the habitable zone is much closer, about a factor of typically 20 or so closer than the Earth-Sun separation. And then for sun-like stars, about a tenth of them have Earth-sized planets based on analysis that was done a couple of years ago. And now with the new data, we could do better statistics. It was not yet done. The results were not publicized yet for the latest observations. And of course, the Keck Observatory was very important, especially with the high-res instrument, in pioneering radial velocity measurements, detections, discoveries of new planets, mostly hot Jupiters, giant planets close in to their host stars. It was found that about 20% of them have such unusual architectures that were not imagined to be common prior to these observations. So again, observations lead the way. Our imagination is much more limited than nature's richness, and so we should always be humbled by what we observe. Speaking as a theorist, right? The most recently, the discovery of Earth-sized planets in the habitable zone of sun-like stars, like the ones I mentioned before, they provided new information about the population of habitable planets. And that was done through a combination of data from Kepler with additional follow-up observations with Keck that revealed that the Earth scale planets come in two flavors. There are two types, ones that look like Earths. They have a size similar to that of the Earth, and those that look more like Neptune. They are mini Neptunes. So we have either super Earths or mini Neptunes. There is a gap or a lack of planets in between, and that has to do with the way they form. So, or with the evaporation of atmospheres by the host stars. If you make a planet that has hydrogen and helium atmospheres, extended atmospheres like Neptune, it's possible that activity or proximity to the host star somehow evaporates those atmospheres in this class. But clearly there are two populations of planets.
Well, if you put Poisson error bars on those, I don't think you will claim so much there are two peaks. We physicists always give you astronomers a hard time about error bars.
Well, it's true that the statistical significance is not large, but the data is already quite suggestive of these two populations. You should look at for details, just have a look. This is a recent paper that came out recently.
He defends next week, yeah.
Will be defended here on Monday.
Square root of 6 is not as
Monday at 11 a.m. BJ Folks.
That's a rate.
Oh, it's a rate, that's not numbered. Then I take it back.
Okay, and of course, in the future, the Keck Planet Finder is being developed. It will have single measurement precision of less than a meter per second, less than a walking speed. And it would allow us to obviously detect Earth-like planets in the habitable zone of sun-like stars, which would be quite exciting. And so this part, Hawaii, is very important in terms of confirming and following up on observations from space. Beyond Kepler, there is the TESS mission that is very shortly expected to be launched, and the James Webb Space Telescope in October 2018, and followed by WFIRST, and some future exoplanet missions that are being planned. And it's always important to keep in mind this interplay between ground-based observations following up on space-based observations, where the apertures are much smaller than we have on the ground. So this was a brief introduction to the current status of exoplanet research. And the basic point that I would like to make is that if you now extrapolate to the rest of the universe from what we know about in our galaxy, then there are 300 billion stars in the Milky Way itself, and there are 3 billion similar sized galaxies in the observable volume of the universe. So altogether, there is 10 to the power 20 habitable Earth-sized planets in the observable volume of the universe. To me, this sounds like a big number. So is it reasonable to assume that life is only realized on our planet? I would think probably not. There are more planets in the observable volume of the universe than grains of sand on all beaches on Earth. And so if you think about the history of humans, there were kings and emperors that were extremely proud to conquer a piece of land on Earth. And they were boasting about it. And this resembles an ant that hugs a grain of sand in a huge beach. I mean, there is every good reason to be modest when you see the big picture. You cannot be too arrogant. So my basic message is that the universe, or astronomy, teaches us modesty. And actually, I wrote a commentary last week that was posted in Scientific American, published last week, entitled "The Case for Cosmic Modesty,"
Excuse me.
which basically makes this point. Yes.
Yeah, I should apologize. A really naive question, but in order for that to be a big number, the number of planets, and that looks like there should be life, don't you need a model of how life happens?
I will discuss yes.
And because it goes against thermodynamics and so on, you need a model that says if the conditions are there, what are the chances? If that's a really small number, then that's not such a big number.
That's right. We don't have a theory for how life emerged on Earth. The origins of life is still an unsolved problem, not to speak about intelligent life. Some people think that it may not exist even now. But what we know are necessary conditions for life, for the chemistry of life as we know it. And I'll discuss those. We need liquid water for the chemistry of life. We need heavy elements. Let me proceed with my talk. At the end of the talk, if you have further questions or comments about it, let me know.
Right.
But it's true that we are missing still some knowledge that will allow us to calibrate which fraction of those 10 to the 20 planets is habitable. You know, what are the prospects for life? And the way I approach this uncertainty is by motivating observations. I think it would be prudent to look at the sky and explore and find out whether life exists out there, rather than argue philosophically or based on prejudice on what we should see. Because if you look at the history of astronomy, it's full of prejudice. People thought that, you know, the sun moves around the Earth, and they didn't even check things. For example, when X-ray astronomy was started, people argued there is no point in building an X-ray telescope because the best we can hope for is detect emission from stars like the sun, you know, X-ray emission. So prejudice is the wrong approach. That's my point. And it's true we have uncertainties, but we should explore. And so that's exactly the argument that I made in this short essay, which is that I don't think that we are special. Whenever we believed in our history that we are special at the center of the universe, we ended up finding that it's not true. And so I don't think we're at the center of the biological universe. Some people do think so. And that has implications for what we do, because if we are not special, then we should find, life is out there, we should just find it. It may be subtle, it may be difficult to detect, but it should be there. And so both primitive and intelligent life should be out there if you adopt this principle of modesty. And we just need to build up the technology. If you look at the LIGO observatory that detected gravitational waves, there was no detection for a long period of time, and people were laughing at those observers trying to detect something until they reach a threshold. And now every month they see an event. Okay, so you need to reach a threshold, and you never know in advance. You can do estimates. And so my point is that once we reach the threshold of detecting either primitive or intelligent life, we would find a lot of signals out there. And it's very easy to dismiss ahead of time and say, let's not look because we know that the Earth is extremely rare, or we know that we are special. And so that's the wrong approach in my view. Now, the only thing that we can imagine right now is life as we know it. Of course, there could be other forms of life that use, for example, ammonia as the liquid rather than water. And so what we know of involves chemistry in liquid water. And liquid water requires an external pressure. If you take ice, you put it in vacuum and you warm it up, it ends up as gas. So in order to have liquid water, you need an external pressure, and an atmosphere provides it. Now, to have an atmosphere, of course, you need to be to have a sufficiently massive planet that keeps the atmosphere, where the gravity is strong enough, and where magnetic fields could protect the atmosphere from the stellar wind. In order to keep the water in liquid phase, you need the planet to be at the right distance from the star so that it's not too hot or too cold. And that's called the habitable zone. So last year, a system of 7 planets were discovered around the star TRAPPIST-1, which is about 10 parsecs away, 3 of which are in the habitable zone at a distance that is of order 10 or 20 times closer to the host star. You can see here the distance. In some cases, it's even closer compared to the solar system. And this is an ultra cool star with about 8% the mass of the sun. So it has a lifetime of about 10 trillion years, 1,000 times longer than the sun. And these planets are close enough to keep themselves warm and potentially have surface temperatures that allow liquid water if they have an atmosphere. So TRAPPIST-1 is a dwarf star that has a lifetime of close to 10 trillion years, which is 1,000 times longer than the sun. So here I plot on this vertical axis the lifetime of the star versus the mass. And the mass of TRAPPIST-1 is 8% of the sun. You can see here the line that delineates the lifetime versus mass for stars on the main sequence.
Do we have any estimate of the age of TRAPPIST-1, how old a star it is?
The estimate is that it's a few billion years old, the order of 5 billion years or so. There is a factor of 1,000 in the lifetime between the smallest, the lowest mass stars and the sun. And then the interesting thing is the sun has roughly a lifetime comparable to the present age of the universe. If you think about the universe, at early times, massive stars had lifetimes similar to the age of the universe. In the future, dwarf stars like TRAPPIST-1 will have an age similar to the age of the universe. And the first stars formed tens of millions of years after the Big Bang. So much earlier. Stars like TRAPPIST-1 will be the last stars to survive in the universe. So let's follow the cosmic history. If you go back in time to a redshift of order 100, the cosmic microwave background had roughly room temperature. That was 15 million years after the Big Bang, just before the first stars formed. So that's a coincidence. The first stars ended up forming, theoretically, according to the standard cosmological model, a little bit later. But if there was a piece of rock with water ice on it, the ice would have been turned into liquid at around that time, just because of the cosmic microwave background. Now, the chemistry of life could not have started earlier because water would have evaporated. So clearly that's the earliest mark that starts the history of life in the universe. And the first stars formed about 50 million years later, with the first planets shortly afterwards, because all you need is massive stars to disperse heavy elements into the surrounding medium in order to be able to make planets shortly afterwards, just a few million years after the massive stars formed. And there is evidence in the halo of the Milky Way galaxy for stars that were born early in the evolution of the universe. These are called carbon-enhanced metal-poor stars. And they have more carbon per heavy elements than the solar composition, but they are metal-poor. And you can imagine planets forming next to them, and these planets would be made mostly of carbon. So one way to figure out what happened in the early universe is to try and see if the Kemp stars, those carbon-enhanced metal-poor stars, have planets next to them. You can look for transits. Nobody is doing it right now, but that's an interesting method. And one can calculate the radius of pure carbon planets as a function of their mass, and also how much of the light they would block if they pass in front of the host star. So that's an interesting observing program that one can follow to figure out what happened at early times. But what I was curious about is, if you look at cosmic history from the time of the first stars to 10 trillion years from now, when the last stars will survive, you can ask, when is life most likely? Is life most likely to be next to a star like the sun today? Or is it more likely to be next to a star like TRAPPIST-1 in the future? And the answer is, if life is possible around low-mass stars, then it's much more likely to exist around stars like TRAPPIST-1 trillions of years from now. And we calculated the likelihood function, and if you allow for habitable planets to exist around low-mass stars, you basically get this black line here that gives you the likelihood per logarithmic time interval as a function of cosmic time, and it peaks around 10 trillion years. If you say that life is possible only around stars like the sun, with a mass of order, the mass of the sun, that's the red line. If you put the lower limit on the mass of the host star to be about 90%, in the case of the red line, 90% of the mass of the sun, and going to any star more massive than that, then obviously the peak is around the present time, around the star like the sun. So if you think that we're not special, then there must be a reason why we're not next to a dwarf star, and it's possible that the star sterilizes. When it's young, it produces a lot of flares, UV flares, and it could sterilize the planets next to it. And that's an interesting conclusion. So life, the preliminary conclusion is that life is most likely to exist around dwarf stars in the distant future, as long as the UV flares or winds from these dwarf stars do not strip the atmospheres of these planets during their youth. And the good, I mean, actually, if you look at TRAPPIST-1, the planets are so close in, that the stellar wind is much more powerful at the location of the planet than it is on Earth. So it's factors of several orders of magnitude stronger stripping than here on Earth. And so that's a real concern. But it's possible that life exists around low-mass stars, and the good news is that we can find out whether that's the case or not by future observations over the coming decade, by observing low-mass stars and looking for the signatures of life around them. And I'll talk about that. Now, aside from the risks associated with being exposed to the UV radiation from a star or due to the stellar wind, there is also a risk from being too close to the center of a galaxy. There is a galactic habitable zone. And being too close to the center implies that the planet could be exposed to flares from the active galactic nucleus, from the black hole at the center. Or there could be stellar collisions, or more supernovae per unit volume, or more gamma ray bursts per unit volume. So we actually did a calculation with a postdoc named John Forbes of what is the likelihood of a planetary atmosphere to be stripped by the X-ray UV illumination from quasars. And we found that about 50% of all the planets lose a Mars atmosphere equivalent in the universe at large. And we did it as a function of the mass of the halo of the galaxy, as a function of the redshift. These are different line types. And for all the stars, or only stars in spheroids, and you see here the fraction of stars that are being affected. And we found that about 50% of all the planets in the universe should lose roughly a Mars atmosphere due to them being exposed to the quasar illumination, X-ray UV illumination. And about 10% would lose an Earth atmosphere, and about 0.2% would lose the entire ocean. There would be enough energy impinging on them to evaporate the oceans that we have on Earth. So a fifth of a percent of the planets in the universe are sterilized by quasars. Because if you lose the ocean, there is no way that you can have life. Extinction by supernova explosions are not as common, actually. We did the calculation in a recent paper that is about to get published in Nature in the coming weeks, where we calculated the probability of a supernova sterilizing a planet. And a supernova needs to be really close to a planet in order to sterilize it. So if you can see here as a function of distance from the center of a Milky Way-like galaxy, and the sun is right here at 8.5 kiloparsecs, what the rate is given by this color code. So we are talking about rates that are 10 to the minus 7 or so per Hubble time of being sterilized by a supernova. And so that's a very small probability, simply because the supernova needs to be extremely close to the planet. Of course, close to the galactic center, the rate is much greater. Another risk to life is asteroid impacts, and we know that dinosaurs were killed by that. But if you do the calculation, again, in the same paper, you find that evaporating the oceans requires a rather rare event that does not happen per Hubble time. There is a small likelihood that it will happen per Hubble time, and therefore, I mean, the likelihood is of the order of 10 to the minus 1 part in a million. And of course, an event that could completely destroy the planet is even rarer than that. That's this dashed line, the second one. So if life forms on a planet, it's really difficult to eliminate it for most of the planets, either by supernovae or by asteroid impacts. It's probably going to be there as long as the star is alive. Now, the existence of life could be best checked in the nearby stars. And here you see an illustration of the nearest stars to the sun. There is the Alpha Centauri system that has 3 stars, Alpha Centauri A and B and Proxima Centauri. It's about 4 light years away. So it takes light 4 years to get to us from that location. Then there are stars farther out. And so the interesting question is there a habitable planet in the Alpha Centauri system? And the answer is yes. A year ago, a habitable planet was discovered next to Proxima Centauri. It's called Proxima Centauri B. The star weighs roughly 12% of the mass of the sun. So again, just like TRAPPIST-1, this is the most common type of star. Just the nearest star to the sun is a dwarf star, and it happens to have a planet 20 times closer to the star than the Earth is to the sun, just in the habitable zone. And the interesting thing is the orbital time is 11 days. So if you happen to be there, you can celebrate a birthday every 11 days. I often advise my wealthy friends to invest in real estate on this planet because the value of real estate will only go up in the future as the Earth becomes inhabitable. The planet is tidally locked, meaning that it shows it shows the same face to the star at all times as it moves around the star. And so it has a permanent day and a permanent night side. You need infrared eyes because the star is relatively cool in order to see well there. And of course, in order to have life on Proxima B, we need an atmosphere. It needs to have an atmosphere. We don't know if it has an atmosphere. But here is a picture I took last week in Maui that led me to realize that since there is a permanent day side and a permanent night side on Proxima B, there is also a permanent sunset ring or strip in between that separates the two sides, where the real estate value should probably peak because it's like watching this sunset forever if you are in that place.
How circular is the orbit?
It depends on the orbit.
Yes. Do we know if it's a circular orbit?
No, but what I was talking about is for a circular orbit.
Yeah.
That's right. We don't know for sure. So does Proxima B have an atmosphere? That's an important question. And the interesting point is that we should be able to find out within a couple of years with the James Webb Space Telescope. And the idea is very simple. As the planet moves around the star, it has a permanent day side and a permanent night side. We are seeing different faces of it, just like faces of the moon as it moves around. And so we're seeing more of the night side when it's in front of the star, more of the day side when it's behind the star. We don't need to resolve it, but since the temperature is higher on the day side than it is on the night side, the temperature contrast allows us to monitor the change in the effective temperature of the planet as it moves around. So we should be able to see the planet changing color as it moves around in its orbit every 11.2 days. And that can be done with a James Webb Space Telescope. We could monitor the day-night contrast in parts per million. And you can see here the precision that one estimates for the James Webb Space Telescope. This is work done with the postdoc Laura Kreitberg at Harvard. And we compare two cases, one in which there is no atmosphere, so you basically calculate the temperature contrast for bare rock between the day side and the night side, compared to a case where there is a 35% heat redistribution between the day side and the night side. It could be either due to the atmosphere or due to an ocean. And you can see how easy it is to separate these two with the future data.
Is that a variation which comes on top of the light from the central star?
Yeah,
I mean,
the variation Okay, yes, that is on
I
top of the emission from the
estimate it
star.
must be an enormous requirement in terms of signal to noise.
That's right. So but keep in mind that this is a dwarf planet, 8%, 12% of the mass of the sun, so it's much fainter than the sun. And of course, here we include that in the calculation. Yeah, that's the main difficulty. Otherwise, it would be a piece of cake even with a small test. So we should be able to tell if there is heat redistribution on the surface of that planet. Now, another way to probe this planet is actually to visit it, to send a probe that will get there. And this is the motivation for the Breakthrough Starshot initiative that was announced in April 2016, about a year and a few months ago. You can see here the person generously decided to fund this initiative, Yuri Milner. He allocated $100 million for the first phase that would last about 5 years, during which the technology that I will describe in a minute will be tested. So it will be a first phase of 5 years where demonstration or feasibility of the technology will be studied at a level of $100 million investment. And the goal of this project is to send a camera that will go close to Proxima B and will send back images of it through a flyby within our lifetime. So as I mentioned before, the star is 4 light years away. It takes light 4 years to get to us. You need to send this spacecraft moving at a fifth of the speed of light in order for it to reach Proxima B in 20 years. How do you launch a spacecraft to 20% the speed of light? That's the challenge, technological challenge. And I was asked to chair the advisory board that includes 35 scientists that leads this project. So I'm working on that. The idea is to basically take the guts of an iPhone or cell phone. If you strip a cell phone from the case and from the human interface, you end up with a gram-scale electronics that has a navigation device, has a camera, has communication device. And so the idea is to build a spacecraft that is gram-scale, attach it to a sail that is being pushed by light, by a laser beam. And so let me start with the motivation, just a short video, and then I'll describe a little more.
We are here. This is home. But for most of our history, we knew only our cradle in the corner. We awakened on this tiny world beneath the blanket of stars, without a note to explain where we come from, who we are. We inhabited a tiny universe, oblivious to the rest of the cosmos. It was only 4 centuries ago that we began to use science to reveal nature's secrets and her laws. What is science? It's an epic journey of discovery. It's a continuity of minds. It's standing on the shoulders of the giants who came before us, looking out across a valley, over a hill, up to the sky, and asking, I wonder what's there.
Oh, that view is tremendous.
It allowed us to look across space and time, see the scale of the universe, and our place in it. We now know that our galaxy alone holds hundreds of billions of stars, and that the visible universe contains at least 100 billion galaxies. In the last decade, we have discovered over 2,000 planets beyond our solar system. It's now estimated that there are tens of billions of habitable planets in our galaxy alone. Are we content to gaze at all these stars, all these worlds, from afar? We have taken to the sky. We have stepped off the earth. have walked on the moon. We have landed on planets and comets and ventured to the edge of deep space. Where now?
So this was the rationale for the project. Basically, the idea is to send a spacecraft to the stars, go beyond the solar system. My personal belief is that once we do that, we will get a message back saying, welcome to the interstellar club, so to speak. And what you see here is a sailboat being pushed by wind. The principle is very similar. Instead of the air molecules bouncing off the sail, one is using photons, bouncing photons off a sail. It's called a light sail. And so the electronics will be attached to a sail that is pushed by a laser beam. And because the beam moves at the speed of light, in principle, you can achieve up to the speed of light using this technology. Most other technologies, you are limited, including nuclear energy sources. You are limited by the amount of energy per unit mass that is being released, which gives you at best a tenth of the speed of light. So this technology is very challenging because it requires the construction of a laser beamer that is very powerful. We're talking about 50 gigawatt over a couple of minutes, delivered to a sail that is being launched to 20% the speed of light across 2 million kilometers, which is 5 times the distance to the moon, roughly. And you need a diffraction limited so that if the sail has a size of a few meters, the beam will have a focus. The spot of the beam will be focused on the sail so that you don't lose power. And the laser beam needs to go through the atmosphere. So there are lots of challenges there in terms of adaptive optics and so forth. It's a cooperative target. It's not a target that you're trying to hit, like missiles. So in that sense, you can design the system such that you make corrections to the atmosphere based on the information you get from the target. And then, of course, the launch itself takes a couple of minutes. There is a period of cruising that takes decades to get to the star, like in the Alpha Centauri system. And then the encounter with a planet passing within an astronomical unit from the planet takes hours. And then it takes 4 more years for the data to get to us. So altogether, we are talking, even in the most optimistic scenario, about 24 years for this information to get to us. But it will be the first step of our civilization going outside the solar system and exploring. And as you know, looking from remotely is very different than actually visiting a place. It's sort of similar to the experience of surfing the web and looking at pictures versus actually going to places on Earth. And so just to summarize the concept, here is without the sound, the concept. There is this laser beamer, there is a sail, and the sail is being released. Oops. Again, the laser beamer. There is a sail that is being released from a mother spacecraft that has a lot of sails in it. Okay, and it releases one sail at a time, once per day. There are hundreds of them. They are very cheap relative to the infrastructure. And then the beamer is producing the beam of light that is pushing on the sail, which is outside the atmosphere. And then within a couple of minutes, the sail is supposed to reach a fraction of the speed of light. And then it makes its journey once the launch ends on a ballistic orbit towards Alpha Centauri system, for example. It takes 20 years to go through the journey. Of course, there are targets of interest along the path in the solar system. One can visit, for example, Pluto within a few days, rather than waiting a decade, like we did with New Horizons. So in principle, this could be an efficient way of exploring the solar system as well. Once the spacecraft gets close to the planet, it takes an image, a photograph, and then sends it back. It takes 4 years for it to reach the Earth. The spot size of the communication from that spacecraft is bigger than the Earth-Sun separation. So it's challenging, and that's one of the challenges, to actually detect the signal. Now, if
How
our
do you get it in the right direction?
you point at the sun, basically. It's easy to see the sun from Alpha Centauri.
Okay.
You just point at the sun because the beam anyway is too big. You don't need to point at the Earth. If our civilization is currently contemplating such a technology, I was wondering whether, if there is another civilization out there that had a billion years head start relative to us. Perhaps they already mastered that technology. And so what would be the signal like if you were to see a beam of radiation that is intended for propulsion? So you can imagine other civilizations launching spacecraft from one planet to another, from Earth to Mars. And if you design a system that is not reaching a fraction of the speed of light, but reaching, let's say, hundreds of kilometers per second, better than chemical propulsion, with an acceleration of only 1g, you find that the best wavelength is actually in the radio. In principle, if there is an observer in the direction of the beam, the observer will see a beam sweeping across the sky and will see a burst of radiation. It will be a flash of radio waves. So we went through the numbers, and you could also see the interference pattern associated with the beam, because there is something blocking it, that's the sail. And we're looking at the leakage of radiation around the sail. So this could be a way of searching for extraterrestrial intelligence, which is looking for signals that are not intended for communication, but intended for propulsion, which could be much more powerful. In fact, we do detect fast radio bursts. We know that at least one of them is originating from the edge of the universe, from a cosmological distance of roughly a gigaparsec. And so if you work through the numbers, it turns out that the amount of power you need, if this was used for propulsion, the amount of power is roughly the power intercepted by the Earth from the sun. So potentially, a very advanced civilization could produce signals that can be detected across the entire universe. If such a powerful beam is necessary for propulsion. I mean, you won't use it for communication because there is no point communicating across billions of light years. You have to wait for the reply billions of years and so forth. The only purpose for making a very powerful beam is for propulsion. But for that, you need to cover the surface of the planet with photovoltaic cells and use the energy from the star to make this powerful beam of radiation. Now, another interesting point that I should mention in the context of planetary systems that have a lot of planets in them is that, for example, in the TRAPPIST-1 system, we have 7 planets, 3 of which are habitable. These are E, F, and G, these 3 planets. So you have 3 rollings of the dice in terms of life forming on one of them. But in addition to that, if life formed on one of them, it could migrate from one planet to the other. This is called panspermia, where life can be transferred from one planet to another, and it's much more likely in a system like TRAPPIST-1, E, F, and G, because the travel time between this system is much more compact than the solar system. So the travel time between planets is 100 times shorter than between Earth and Mars, for example. There is the conjecture that perhaps life was transferred between Earth and Mars. And then the chance of hitting the target is also much greater. It's about 20 times larger than for Earth and Mars. So altogether, you have a much higher probability for panspermia in the TRAPPIST-1 system. That's something to keep in mind. And we wrote a paper about it, making analogy with immigration of life forms between neighboring islands. So if you examine islands on Earth, there is a theory behind how life may have migrated. And the same can be applied to planets, exoplanets. And if there is panspermia, of course, you expect much more clustering. Suppose we find life on planets in different places, we can see if those places are randomly distributed in space or they are correlated, clustered. Clustering would inform us of the possibility of panspermia, transfer of life through rocks that were ejected from a planet due to the impact of asteroids, for example. And so clustering of life could be indicative of panspermia. In principle, life could be transported not only between stellar systems, but also between galaxies. When you have two galaxies coming together, and if each of the galaxies has a black hole at its center, when the two black holes come close to each other, the binary black hole system ejects stars from the galaxy. And those stars can travel cosmological distances and reach other galaxies. So we actually calculated that there are stars reaching up to the speed of light, in principle, filling up the universe. There is a sea of stars moving through the universe that were ejected from such a process, and we calculated the abundance of them. Now, detecting signatures of life in the atmospheres of planets would be a highlight of future observations, where if you have a transit, a planet that goes in front of the star, you can look at the light that goes through the atmosphere of the planet and search for the fingerprints of molecules in that atmosphere. And in particular, molecular oxygen, it would disappear from Earth's atmosphere within 1 million years if life ceased today. And so molecular oxygen is a very good indicator of life, although it could be produced also by natural mechanisms. So you need a reducing gas like methane, for example, together with oxygen and together with other molecules to provide an indication for life. The reason it's difficult to detect those molecular fingerprints is because the size of the Earth is much smaller than the size of the Sun, and the atmosphere is even a smaller cross-sectional area than the Earth. And so when an Earth-like planet passes in front of a Sun-like star, you get only 1 part in 10,000 of the light to be blocked by the Earth itself, and then an even tinier fraction of that light to go through the atmosphere. So it's a very challenging prospect to actually look for the molecular absorption due to the atmosphere of the planet. However, we know that the Sun, within 7 billion years, will end its life and eventually become a white dwarf. And there are lots of white dwarfs around. And a white dwarf has roughly the size of the Earth. So if you happen to have a transiting Earth-like planet around the white dwarf, it would block a significant fraction of the white dwarf light. You may ask, what is the habitable zone around a white dwarf? Turns out that after a few billion years, a white dwarf cools to 6,000 degrees roughly. And the habitable zone is about 100 times closer to a white dwarf than it is for the Sun. The orbital time there is about 10 hours. And the transit duration is about 2 minutes. We just don't know about planets transiting white dwarfs. Nobody did the survey of white dwarfs to look for transiting planets. But if any example is found, it would be of a planet that is orbiting 10 hours with a 10-hour orbital period. That would be a fantastic opportunity to look for signatures in the atmosphere of that planet. And of course, you may ask whether such planets are formed near white dwarfs. We do have evidence for rocky material around white dwarfs. And whether life could exist around a white dwarf, we don't know. But interestingly enough, it should be possible with JWST to detect molecular oxygen on a habitable planet around white dwarf if we know where to look for it. It requires 5 hours of total integration time of all the many transits, altogether summing up to about 5 hours to be able to pick up the oxygen absorption features with James Webb. One could, in principle, even look for industrial pollution, for molecules produced by a civilization that are not produced naturally. You could imagine a civilization basically terraforming a planet, changing the condition on a planet that was too cold to host life, to make it warmer, to make intentional global warming, so to speak. And some of the molecules survive, like CFCs, they survive 10,000 years. So even after civilization is dead, it kills itself, you could still find the traces, the molecules that are there. And so we actually did a calculation that potentially if the pollution is 100 times more than on Earth, then around the white dwarf you could detect it. Another artificial thing that you can find on a planet is a spectral edge. So Earth, for example, has vegetation, and that produces a very high reflectance longward, at wavelengths longer than 0.7 micron, because the plants and the vegetation does not need these photons. They basically reflect those photons. They use up only the ultraviolet photons. And so you get a very sharp rise in the reflectance of leaves around 0.7 micron. The same happens for photovoltaic cells, for solar cells that are made of silicon. You can see here the reflectivity as a function of wavelength. There is a sharp edge. So if a civilization is covering a planet with solar cells, then in principle that would have a signature in the form of a spectral edge. And one can monitor this spectral edge as the planet moves around the star, because one sees different faces of the planet from a distance. So if there is a tidally locked planet, the day side, the permanent day side, may be covered with silicon, trying to harness all this power and transfer it to the night side, illuminating the night side potentially, and allowing vegetation to grow there. And you can look for the spectral edge contrast if only one hemisphere of the planet is being covered with solar cells. You can see the variation as the planet moves around, the variation in this amplitude of the spectral edge, because only 1/2 of the planet is covered with it. So altogether, I just wanted to convey the sentiment that we live in an exciting time where we are starting to search with very exquisite sensitivity with new instruments for life, either primitive life or intelligent life. And stay tuned, the next decades should be quite exciting if life is out there, and we will find it. Thank you very much.
All right, let's start with the question, John.
So I just wanted to point out that the same BJ Fulton who found the double dip in the planets, for a first-year project, he actually did look for transits of planets around white dwarfs using pan-stars.
Oh, that's wonderful.
Yeah, I can't remember the limit.
How many?
Didn't find any.
Okay.
I can't remember the limit is.
Well, about a quarter of the white dwarfs show evidence for rocky
That's right.
debris in the material that came from rocks that is on their atmospheres, that would have sunk in by diffusion if it were not replenished quickly.
Right.
And there is even a system where you see the breakup of an asteroid to a bunch of,
Rolf,
But I would have to say so that such a planet nearby to white dwarf would have gone to a rough time in its life.
That's right.
With a former star becoming a red giant, supergiant, asymptotic giant star with tremendous stellar winds, a super wind, planetary nebula ejection, you name it. So what you wonder, whatever life would have existed.
No, so the idea is that the planets could form, for example, from the planetary nebula. The material would make a second generation of planets.
Okay.
And we know about planets around neutron stars. You would expect that to be much more violent when you have a supernova explosion, right? And nevertheless, we find planets near neutron stars, near pulsars. Okay, they were actually the first planets discovered. Now there are reports of planets for post giant phase. There is a Nature paper from 2013 reporting the detection of planets after the giant phase of a star. And there is this evidence for rocky material. And so in my book, if there is rocky material planetesimals, it's likely that you could make a planet. And since there are so many white dwarfs, the only question is what is the statistics? What's the likelihood of how many planets are there? Yeah. And it could be that it's only a small fraction of all the white dwarfs, but we should check. Now, on top of that, we need to find systems where the planet actually is going in front of the white dwarf. But that has a high likelihood because the white dwarf is, the habitable zone is relatively close to the white dwarf. It's a few times. So it's a few times, it's of order the radius of the sun is 10 to the 11. So it's about a few times the tidal disruption distance from the white dwarf. And so at that distance, the probability of the right inclination is quite substantial.
Plus, there's the probability that a civilization like ours moves to such a place once the sun goes red giant.
That's right. There is a possibility. If you ask, we tend to think that we should look for intelligent civilizations near stars, but once the technology develops to a high enough level, it's likely that most of the signatures of intelligence will be completely separated from the stars because there would be all these robots or spacecrafts carrying the information to other places. And then the issue is that it's not easy to detect those things because even if I did a back of the envelope estimate once, a nuclear war on the nearest planet would not be detectable with the biggest telescopes we have right now. And the signals may be very subtle because the amount of power, the luminosity of such small objects would be quite small. So although we tend to search for things around stars, it's quite possible that there are objects flying through space that carry that signal of other civilizations that are much more common, but are difficult for us to detect. And then there is the Fermi paradox. Why haven't we heard from them? Where is everybody? And my tendency is to think that we are not significant enough. That when you walk down the street and there are ants on the pavement, you step on, you just don't care. We are such a primitive form of life, that is so common that it doesn't seem like a worthy target for communication or special attention. Or they have their own goals. But that's a speculation. There are many possible solutions to the Fermi paradox.
Jonathan had a question.
Yes.
So that was just a comment actually, and then regarding the falsehood and Tonry paper. But no, I wanted to ask about why radio wavelengths are the best for propelling these sails.
Okay.
I like the idea of covering the planet
so
with
for
radio.
Starshot, it's actually It all depends on the acceleration that you are tolerating on the
Right.
spacecraft. If you have 1 gram of electronics, you don't care how large the acceleration, as long as it's not more than 1,000,000 G. The electronics can sustain it. So with Starshot, we have 60,000 G over 2 minutes. That reaches 0.2. Just as a ballpark number, 1 G times 1 year is the speed of light. Keep that in mind. So to get to the speed of light, all you need is to feel exactly what we feel now on the surface of the Earth for a year. If you're sit on a spacecraft that is accelerating, it would feel just like gravity on Earth, right? Because according to Einstein, gravity and rocket acceleration is the same, right? So we could sit here and feel just like for a year you would reach the speed of light. Now, if you want to reach the speed of light within minutes, then you need hundreds of thousands of G. And so if you want, for example, to carry humans, I mean, we know that even the bravest pilots that use fighter jets, they can tolerate maybe 10 G, okay? But if you limit yourself to 1 G because the creatures that you are transferring were born on the surface of a planet with a surface gravity of 1 G, then you are accelerating very slowly for a long time, and therefore also the distance goes.
Yes, you're light year away.
And then it turns out, so you can calculate what is the optimal wavelength, okay? And the wavelength depends on the distance over which you need to accelerate the spacecraft to its terminal speed, okay? Because you are using diffraction limited optics, right? So it's the Fresnel distance associated with the wavelength that you're choosing that has to match the acceleration distance. And when you go through the math, it's very simple math. You just need to use diffraction limit optics.
Okay.
And the size of the sail per unit mass. And you end up that if you want to accelerate at 1 G, radio waves are the best. Okay, radio waves. If you want to accelerate, if you're not limited in acceleration, then for us, for example, in Starshot, it's actually 1 micron wavelength. We want it to pass through the atmosphere, but it needs to be shorter wavelength because otherwise, so we are thinking about a beamer that is 1 kilometer in size. If you make the wavelength larger, then you need to make the beamer larger to keep the same focusing, and it becomes much more complicated.
You don't think the UN will have a problem with you building a 50 gigawatt 1 micron phase laser?
So if you were to put it in space, it would, yeah, actually I was told by many people that the policy issues, the issues of international collaboration, political concern, is more difficult to solve than the technological aspect of the project. I mean, if you put it on Earth, it's less of a weapon because, I mean, you could reflect it from a mirror, but it's not as easy. And you can make all the guarantees that there will be, supervision of how it's being used on the ground and so forth.
Right.
And indeed, it's a concern. That's part of the challenge that we have with this project. The idea is to have an international project that involves many countries and that people see as a scientific project. The total cost would be at the end similar to that of CERN or JWST. We're talking about a significant project that potentially funded by both the private sector and governments. Right now, it's just the private sector, but once the technology is demonstrated, the next phase would be a scaled up a scaled up version of the funding by a factor of 10 or so, where there will be a system that is a miniature of the final system that is just used for demonstration. But that will probably require 10 times more than what we currently have, 100 million.
Okay.
To do.
We're running into lunchtime. One more question before.
So you just addressed the concerns that this thing could be used as a weapon, presumably to destroy a spacecraft. How do we prevent it from destroying the spacecraft that it's supposed to push?
That's one of the important. We wrote down a list of 20 challenges, and that's in my book. That's perhaps the highest priority challenge because we are illuminating with 100 gigawatt an area of a few meters in size, okay, and 99.999% of that light needs to be either reflected or transmitted, but not absorbed. So the absorption needs to be less than 1 part in 100,000. Okay, because otherwise you would overheat or ablate or explode the surface. It will be just like the story of Icarus that came too close to the sun, so the wax melted and he lost his wings. And so it turns out that this, after looking at the literature and speaking to people that work on materials, that this ends up being actually a doable thing, because it turns out that there are materials that reflect that, at least on paper, they could achieve 99.999% reflectivity, and over a broad range of wavelengths. So there seem to be, we haven't started yet the demonstration, but there seems to be a path forward. I wouldn't say that it's a showstopper. Right now, I'm more worried about other aspects of the project, but this was the one that I was worried about the most. So in fact, Yuri Milner went around the table of the people involved and asked each of them to say what they're worried about, and I mentioned this risk. Yeah.
Let's thank Avi once more. We're going to be going to lunch at Cardano. I guess we'll meet back